So hello everyone, welcome to the Introduction to Deep Learning for Materials Design. This workshop is part of a workshop series about data management for material scientists, and you can find the other workshops recording at materialpioneers.com. I'm also going to put the link in the chat so you can also reach out to the other workshops. The workshop series are the result of a joint effort between 40U Research Data, TU Delft Library, Open Science Community Delft, and Material Pioneers. Today, our trainer is Kumar, assistant professor at TU Delft in the Department of Material Science and Engineering. A few practical information. There will be 3 sessions. Each of the one will have a demo, exercises, and a break. Please feel free to post your questions in the chat so the trainer will answer them after the end of each session. I would also like to tell everybody that this session will be recorded, also to allow some other people to watch it afterwards. And if you don't feel comfortable being recorded, please let us know, or you can just very simply turn your camera off. The breakout rooms will not be recorded. The only thing that will be recorded is the introduction by Sid. And say that, I think I can leave the floor to Sid. Thank you so much.
Thank you, Alessandro, for the introduction. All right, so I think Alessandro just shared a Dropbox link in the chat. Was everyone able to download the files? If anyone who was not able to access the files, please let me know. Otherwise, we move on. And if you have downloaded the files, can you please open the file named session 1A notebook .ipynb in your Jupyter lab. And if anyone has an issue at this point, just please let me know. Session 1A. All good? Does anyone still need some more time? Okay, then I'll assume everyone has the session 1A notebook open in their browsers, which means we can get started. Okay, so first of all, welcome everyone to this workshop on Introduction to Machine Learning or Deep Learning for Materials Design. This is an introductory level workshop meant to be a first step towards exploring how machine learning can accelerate materials design, and is already doing that across academia and industry for several research problems. So the learning objectives for our workshop are going to be this. At the end of this workshop, you should be able to use PyTorch for basic tensor manipulations, as well as automatic differentiation. You should be able to create and train neural networks and understand their basics and preliminaries for machine learning, and then later on contextualize that in the domain of material science. And finally, we'll end the workshop with a simple research case study so that you can learn how you can deploy simple neural networks for material design problems. Okay. The plan of the workshop is as follows. It's divided into 3 sessions. Each session is supposed to last approximately 1 hour to 1 hour 15 minutes. We will start with session 1, which is on PyTorch basics, tensors, automatic differentiation. The next session will be on the introduction to neural networks, how to implement them, how to train them. And finally, we'll end the workshop with, as I mentioned earlier, a case study on deploying neural networks for designing materials. Okay. With that being said, let's get started. So in your notebook, you'll see I've already put in some import commands. These import commands are used to import your libraries. The important libraries that we'll be using today is Torch or PyTorch. This is the most important library we will be using for all kinds of things related to neural networks today. Numpy, you might be familiar. It's one of the most ubiquitous packages in Python for all kinds of numerical manipulations, creating arrays, and so on. And finally, we have matplotlib, and this is for all kinds of plotting. And finally, we will be dealing with random numbers. So I've just set a manual seed. This is to make sure that all your results are reproducible, even if you have random numbers at play. Okay, so let's start with the basics of PyTorch, which is how to create a tensor. So tensor is similar to an array, but the only difference is that it can be multidimensional. Okay, so if you want to, let's say, create a tensor from a list, let's say you have a list of numbers 1, 2, 3, and 4. You can simply say x equals torch.tensor 1, 2, 3, 4. And if you run this cell, if you run this cell, you should be able to see that you now have a tensor x with all the numbers arranged in a 2D array format. Okay. Then we go one step further. Let's say you don't have a list, but you have a Numpy array. So very similar to the before, you can say x is a torch, or maybe we start with array. So arr is np.array 1, 2, and 4. Okay, so this is our Numpy array, and then we can say x is torch.tensor arr. All right. Again, we have our tensor here. Okay. This was creating a tensor when you know the entries, but let's say you want to create a simple tensor, 3x3 tensor with all zeros. So you can simply say x equals torch dot zeros 3, 3, and you have your tensor here. Okay. Let's say you want to create a tensor with random entries, and these random entries are sampled uniformly from 0 to 1. And you would say x equals torch.rand. And here you'll specify again 3x3. You have a random tensor. So just different ways of creating tensors in PyTorch. You can now start accessing certain entries, certain rows or columns of this X tensor. This is very similar to how you would do it in, for example, Python or MATLAB or any other software. You would say y equals, let's say, x. A colon denotes all rows, and you can say 0 to 2. So this means the 0 and the first column. And so if you execute this, you now see you have the first 2 columns of the tensor x. Okay. You have a tensor in PyTorch, you can always convert it back to NumPy. You can just simply say arr equals whatever your tensor is, let's say x. I can say x.numpy, and now it's converted into a NumPy array. And here I'm printing the array, and here I'm also printing the type of the array. Okay. Please let me know if I'm going too fast or not. I would appreciate any feedback during the demo as well. Okay, so now we have tensors. Let's try to operate on these tensors. Okay, so let's say I have a tensor x, 1, 2, 3, 4 again. I have some tensor y in which I've multiplied 0.1. So if I print these two arrays, I have 1, 2, 3, 4, I have 0.1, 0.2, 0.3, and 0.4. Let's add these arrays. So if I say simply x plus y, you see that the addition is element-wise, okay? And this is actually true for almost all default operations, okay? So most default operations are element-wise unless specified otherwise. We can do a multiplication. So if I say x multiplied y, now keep in mind, these are matrices, these are tensors, but this multiply sign means element-wise multiplication. It's not a matrix multiplication, okay? Simply we can do x divided by y, and we get 10, okay? So that was element-wise multiplication, but you can also do matrix multiplications. So let's say you have a x tensor, which is size 10, 3, and you have a y tensor, which is size 3, 5, and you can simply say x at y. So this add symbol, it's a shortcut for matrix multiplications. Sorry. And I can assign it to z. Okay, so I get the z tensor here, and if you look at the size, it's 10, 5. So if you go back to your linear algebra, if you multiply a tensor of size 10, 3 with a tensor of size 3, 5, the final size of the product will be 10, 5, which is exactly what we get. Okay. Any questions at this point? No?
No.
Sounds good. All right, so here it gets a little bit tricky, and I'll try to explain why. So you're familiar with the equal sign. This equal sign is the assignment operator, okay? So let's say I created a tensor x, a simple 1D tensor with the entries 1, 2, 3, 4. Okay, I assign it to another tensor, let's say z, so z equals x. And then let's say I modify the 0th entry of z to, let's say 5, okay? So I created x, assign it to z, modify z, okay? If I check the values now, I have 5, 2, 3, 4 for z, which is expected. But look what happened with x. The entry of x got modified as well. Instead of 1, you now have a 5. So the problem here is that assignment does not create a new tensor. It only creates an alias or a reference to the tensor, and modifying this reference will modify the original tensor as well. So the way to fix that, or the way to avoid these kind of problems, is to say you have your tensor x, let's say tensor 1, 2, 3, 4, okay? Instead of using assignment or the equal to sign, I'll say z equals, z equals x dot clone. And instead of assignment, I use the clone operator, and I say z, I modify z again. So I say z0 is 5. And now if I check the values, you see z has been modified, but x has not. So the takeaway message is that assignments with equal only create an alias. And if you modify this alias, the original also gets modified, and vice versa, okay? And the other takeaway is that if you use clone to create a copy of a tensor without modification, you can then rectify this issue, okay? Now, doesn't mean you have to use clone at all times. If I say z equals, let's say, x plus 5, then I don't, theoretically, I can do clone here, but that's not necessary. As long as you're doing some modification and then doing an assignment, then x does not get modified. Only if you use the assignment itself without any modification is when you have a problem with assignment operator. Okay, So that brings us to the end of part A of this session. If you have any questions, please feel free to shoot. No? All clear? Okay. So then we go to the next notebook, which is session 1B. And you'll have the chance to go through the notebook yourself. Whatever I'm doing here, it's already in the notebooks that you have. So again, we start with some inputs. But the next topic that I'd like to discuss is what's called a computational graph. And this is why we need a special software like PyTorch. So what is a computational graph? Now, any computations you do in Python, MATLAB, whatever, can always be, no matter how complex it is, can always be broken down into a bunch of elementary operations like additions, subtractions, multiplications, divisions, and so on. So let's say here we start with two variables, x and y. Okay. Now using x, I multiply 2 to it, I get 2x. Okay. At the same time, I can take x and y and I can do an addition operation on both and I get x plus y. Then I can take x plus y with a positive sign. I can take 2x with a negative sign. In other words, I'm subtracting these two variables such that I get z equals minus x plus y. Okay. So computational graph is nothing but storing each and every operation that you did, starting from some initial variables to arrive at a final variable, in this case, z. Now, the question is, why would you want to keep track of all of these operations to arrive from your starting point to your final destination in this computation? And the answer is what's called automatic differentiation. Eventually, what we want to do is to be able to differentiate this z with respect to this x and y. And imagine in real life, you will have a very, very complex operations, complex functions in the middle, and it's really not possible for you to get the gradient of z with respect to x and y analytically. But if you have been tracking every single elementary operation, you can always use chain rule, which you've studied in calculus in your undergraduate at some point. You can use chain rule to work your way back through each of those elementary operations and be able to compute the derivative of z with respect to x and y. Now, before I show you how it's done in terms of implementation, I just want to take a second and ask if anyone has a question about this computational graph concept. All clear? Any questions? Okay. All right, so far good. All right, thanks. So now you have this computational graph. We will use this as an example to differentiate z with respect to x and y. Okay, and let me bring up my notes. Yeah. So let's start with a tensor x. Okay, so torch.tensor. Let's call it minus 3.5. All right. And then I create another tensor y. Let's call it torch.tensor 5. Then I print x and y. Okay. Same thing as before. You have two tensors, nothing special. But let's do a couple things. I can recreate this tensor. So torch.tensor minus 3.5. But this time I add an additional parameter here called requires grad equals true. And I can do the same for y. Okay, so you see the difference now. Here you just have the tensor with its value. But now you have a tensor with an additional parameter or an argument here called requires grad equals true. And this requires grad denotes that any operation on this x and y will now be tracked so that eventually you can be able to compute the gradient. If you don't set this requires grad equal to true, then gradients will not be tracked later on. Okay. So let's create two intermediate variables based on the graph that we had. So we will create 2x and we will create x plus y. Okay. So let's say var1 is 2x, var2 is x plus y. And let's see what we get. We get var1, which is simply x, twice the value of x. So minus 3.5 becomes 7. X plus y, 5 minus 3.5, you get 1.5. But what's interesting is now you have another argument here, grad function. So this is the tracking part. So for the first case, the grad function is multiply backwards, which means it's tracking that for var1, the way you arrived at var1 was by doing a multiplication on something that was before var1 in this computational graph. Similarly for var2, you see the grad function is now addition backward, which means this var2 was achieved by doing additions on two different numbers, which it is storing internally. And so this is what exactly I was talking about. X and y are the variables you're starting from. And all of these intermediate variables, you're tracking which operations were used to get there. Okay, so you have var1, var2, you can simply say now that you want to compute z. So you can say z equals minus var1 plus var2. And now let's print it. You get your final value of z, and you see again a grad function addition backwards. Okay, so at this point, you have a computational graph stored internally where from x and y, you can go to z by tracking each and every operation. Now let's, from z, go back to x and y, compute the derivative using chain rule, but you don't have to do it manually. This is where PyTorch comes in, and it will do it automatically for you. So if you simply say z dot backward, and that's the keyword you have to remember, this backward function. If you do z dot backward, the gradients have been computed already. You don't see them, but they have been computed. And these gradients are actually stored where for the variables that you were tracking. So the two variables that you were tracking were x and y, right? X and y here. So if you simply now type x dot grad dz over dx will be your x dot grad, and dz over dy will be your y dot grad. Okay. So what's happened here is you did the differentiation from z. So you started going backward from z, and it ended up on x and y where the gradients were stored. And if I execute this cell, you get your gradients. Okay. So the key functions that you have to remember is you start with requires grad. You say that we will track these variables. Then you do your operations on it. And then ultimately you do backward. So you, with your final variable z, you do a backward, it will compute your gradients, and then you can extract those gradients using the variables that you were tracking. So in this case, x and y. Okay. Now the key thing here is, and this is an implementation peculiarity, that the backward can only be called once. After calling backward, the computational graph is destroyed. So if I execute this and then I try to execute it again, then I will get an error. Maybe we can try. And you see, you get an error saying trying to backward through a graph a second time is not allowed because the graph has been destroyed. There are workarounds for it, but in the most default case, that's not the case. And the second point is that backward can only be called on a scalar. So the final variable z, it has to be a scalar, but the initial variables, in this case, x and y, they can be multidimensional tensors, vectors, whatever. Okay. Again, there are workarounds for having z as a tensor, but we're not going to cover it here. Okay. So let's consider a more complicated case. So let's say we create two random tensors. Let's say a equals torch.rand. Let's say 10, 4 requires grad equals true. Okay, so an array A of size 10, 4 with requires grad equal true for gradient tracking. Sorry, my bad. Let's define another one. So torch dot rand 10, 2 requires grad equals true. So you now have two random tensors A and B of different sizes. I can create a new scalar. It has to be a scalar, remember? So C is torch dot norm. Torch dot, let's say, sign. We can do A all rows 0, 2. Let's maybe end it here, plus B times B. Okay, what's the problem? Interesting. Give me a second. That's strange. Let's maybe try again. So A is torch.rand 10, 4 requires grad equals true. We can print A. Okay.
For B, you have a type of requires.
Oh, yeah, sorry, my bad. Yeah, there you go. Okay, so you have A, B, which are two tensors. You can now create a complex function from A and B. You can even have, for example, a sign operation in here. One thing you have to keep in mind, all of these operations have to be either elementary or functions defined by torch. You cannot take your PyTorch tensor, convert it to Numpy, and then convert it back to PyTorch and expect the gradient tracking to work, because all these operations have to be tracked. Okay, so you create your C, you get a number here. Now we can do a backward gradient. So we do C.grad, C.backward. Okay, so you can do C.backward and then your gradients will be stored at A and B. So if you do A.grad and if you do B.grad, there you go. So A.grad and A.grad and B.grad give you your tensor gradients, which are here. And you can see the gradients, when I created C, it was not a function of the last two columns of A. Therefore, the last two columns of the gradient are also 0. Okay. All right. So that was simple automatic differentiation. We can use this automatic differentiation to now do some kind of optimization. And before I go to optimization, I'll just take a minute to ask for any questions. Anyone? All clear? Okay. So the whole purpose of automatic differentiation is that we want to try gradients so that we can do optimization problems. And for this, we will consider a very simple line fitting or curve fitting example In this example, in this demo, I'll consider a line, but in the exercise session, we'll look at a little bit more complex case of a quadratic function. And we need to keep in mind, why are we looking at line fitting here? Because essentially, in the end, we will replace this linear equation with a much more complex function in the form of a neural network. Okay. So let's say you have some data, okay? So you have some data X for which you have some measurements Y. And in machine learning, usually this data is called features, whereas the measurements Y are called labels. And this is a very common terminology. Features are your inputs, labels are your predictions, or your output, or your observed values, okay? So let's create a simple tensor. So torch.tensor. Say 1, 2, 3, 4, 5, and 6. Okay. So just some points where you're measuring your Y. And let's say the Y true. So these are your true measurements, is 3 times X. Okay, it's very simple. Let's plot X versus Y true. Okay, so on X-axis you have X, on Y you have your measurements, and these are the points where you have your measured values. Now let's say you have a function that you would like to fit. So Y equals f of X, and I assume it to be a linear function, so alpha X, and alpha is what I want to determine. Okay. So what I'll say here is now alpha is torch.tensor, and I'll give it an initial guess of 0. It's a bad one, but it's just an initial guess, and we'll try to optimize for it. Requires grad equals true. Okay, so this alpha in our model that we assume, alpha times X, this alpha is the unknown that we want to find. And therefore, I'm going to be tracking its gradient. So requires grad is true. Okay. Now let's make a prediction. So I say Y pred is alpha times X. Okay, so this is my prediction based on whatever alpha I guessed. I can compute an error compared to my measurements, my true values of Y. So I can say loss. Loss is another term for error that we like to use in machine learning terminology. So I say torch.norm. Norm is just the L2 distance. Okay, so torch.norm, Y prediction minus Y true, and that's it. So the squared, the sum of squared errors, and then I take a square root. So that's the norm. Okay. And this is what I get. So my Y predictions are all going to be 0 because alpha, my guess for alpha was 0. This is your Y true. And this is the total error that you have in your predictions. So let's try to optimize for this alpha. Let's define an empty list where we will be storing the error as we try to optimize for alpha iteratively. So it's just going to be an empty list. Let's define a learning rate, and I'll come back to what this learning rate is in a couple of minutes. So let's just say it's just a constant LR learning rate 0.01. I can define my alphas again, similar to before. So alpha is torch.tensor 0 requires grad equals true. Okay. Alternatively, I can also not do this and define my alpha, and then I can say alpha dot requires grad true. So instead of specifying requires grad true at the time of creation, I can also set it to true later on. Okay. So let's try to write an optimization loop where we will be iteratively optimizing this value of alpha starting from the initial guess 0. So we make a prediction. So y pred equals alpha times x. Similar to before, we will compute our error. So we say loss equals torch.norm y pred minus y true. Okay, let's store this loss in this loss history array or list for future, just so we can see if our optimization worked or not. So I can say loss history dot append. I can say loss dot detach dot item. I'll tell you what these mean. So loss is the term that you just predicted. Because alpha is for alpha, the requires grad is true, which means every operation is being tracked, which means y prediction is part of a computational graph, which means loss is now part of this computational graph. So loss.detach means just take the value out of the computational graph and then take out the item therein and append it to this list. This list is just for post-processing. We don't want to store the whole computational graph inside this post-processing array, okay? But that doesn't mean that loss is out of the computational graph at this point, okay? So now comes the most important part, which is we will compute the gradients. So we say simply loss.backward. And this. So when you say loss.backward, what happens is PyTorch goes to the computational graph starting from loss. It goes all the way back to where it started, which is alpha. And it will compute the gradient d loss over d alpha. Okay. So now we can use that gradient information to update the value of alpha. So we can say alpha minus equals. So minus equals is basically saying it decrease the value of alpha by this amount. And this amount will be LR times alpha.grad. So let's do a recap. Alpha.grad is the gradient of the loss with respect to alpha. LR is just a coefficient saying, I don't want to make a very big change. Whatever this alpha gradient is, just scale it by a factor of 0.01. This will be my sort of iterative change in alpha that I want. And I update my new alpha by decrementing this value. Okay. What is this? This line says that for the next few operations, everything that is under this part, torch.noGrad, please do not do any gradient tracking. Please do not do any computational graph updating or so on. And why do we not want to do that? Well, you see, alpha is, if you were tracking the computational graph, then alpha is on the right side, alpha is on the left side. The computational graph will end up having a loop. Okay, we don't want that. We don't want alpha to go around and then come back to itself. The alpha.grad information is there. We don't need to do anything else. So therefore we stop our gradient tracking. Okay, now you have updated your alpha. This alpha.grad information is now useless to us. It's old information. Our alpha has been updated. So we simply say alpha.grad.0. And this 0 function basically says set all the gradient informations to 0. Okay, so you started with your learning rate, your alpha, you started gradient tracking, you made a prediction, computed the loss, differentiated the loss with respect to alpha, updated the alpha, remove all the all the gradient information, the old gradient information, because that's now useless. And you do this 100 times. Could be 1,000, could be 10,000, that's up to you. Okay, so let's compute that. That's it. Now, this loss history, I remember I told you it's just a post-processing thing. We want to see how the loss changed over optimization. And if I just do the plot, so on x-axis, I have my iteration number. On y-axis, on the log scale, I have my error. And you see the error started decreasing as we went up our iterations. Around 25 or 30th iteration, our error is almost very, very small. It has saturated. And we could have stopped our iteration at step 40, but it's okay, we let it run until 100. Okay, so now let's check the value of alpha. And you see, alpha is 3.0526, which is very close to the true value of alpha, which was 3. Okay, so we started from 0 for alpha, we ended up at 3. And we can now make our final predictions for alpha. So I can simply say y pred equals alpha x, right? Alpha times x. And I can do a detach here because I don't want the computational graph. I can do my plotting. Blue points are the original measurements. Orange line is the true value, is the predicted function that we learned. Okay. So that was a very simple curve fitting example of using automatic differentiation, using PyTorch to do a gradient-based optimization and learn a function.